board.
What do you got? What do you got in mind there? Comets.
Yeah.
All right.
So we have some more eccentricity, like we did with ellipses, but now it's a hyperbola, so it's a slightly different formula.
I like eccentricity.
I do too, and it still has something to do with how eccentric our curve is, how wide or whatever. But it's not quite as obvious. I feel like ellipses, it's like, oh, well, if on one end you have a circle, the other end you're going to have a really
an oval. Yeah, an oval as they teach the little children.
But in this case, I don't actually know what's going on with it. So,
I guess maybe it's talking about, wideness and narrowness still.
Yes, but these will be values bigger than 1 if it's
Of course they will. Yes, of course they will.
Now we've got this problem here.
All right,
it's quite a problem. It's talking about a comet following a hyperbolic path. Did you know that comets follow a hyperbolic path?
You started talking about hyperbolic, and I started playing 2048. Sorry.
That's helpful.
Sorry.
So a comet actually follows a hyperbolic path. If you can imagine, basically, here's my xy axis and here's my center point for my hyperbola. And so over here, if our hyperbola looks like this U-shaped curve, okay, well, whatever it's going around, I'm going to pick orange, whatever it's going around, that foci, that's like our sun. Like here's our sun, which is the focus of this hyperbola.
Right.
The comet follows this hyperbolic path. So
right.
That's kind of neat. So that's what's happening in here. Now remember perihelion.
Now this is for a one-time only sort of comet, I would think. Otherwise it'd be more elliptical, correct?
I don't really know how that works. Maybe it does a hyperbola until it gets close to another sun and then does a hyperbola around that.
Isn't that an ellipse then?
Not necessarily.
I mean, I don't know.
Because then what if it goes this way and then it just turns around?
Just like puts on the brakes and changes directions?
Yeah. No, gravity. It doesn't have brakes. We're not comet experts. Okay, so so it has a perihelion distance, which last time we defined as the distance closest to
zero. Closest to zero.
No.
Closest to the focal point, sorry.
Yeah, so
it's
in
the
our
point on
here,
the hyperbola closest to the sun.
Right. We've got 90 here. And so let's think about what our different letters mean. For example, if this would be a vertices, and so the line in between there, right here, that's A.
Right.
Because we take our center and add
from
A.
the center to the vertex, yes.
And then to get to our focus, we take from the center to the focus, and that's C.
Right.
Okay.
And there's a couple different ways to recognize this.
Right.
One of the ways is we could say that A plus 90 is C.
Right.
Or we could say that C minus A is 90, depending on what we need.
Right. That's basically what we're getting from this first sentence. Then it tells us that when the line from the comet to the sun is perpendicular to the focal axis of the orbit, the comet is 281.25 gigameters from the sun. Now that line is perpendicular to the focal axis. Or not to the focal axis.
Yeah, to the focal axis, yeah.
Oh, the focal axis is this way, and so perpendicular gives us this. So
right.
That's 281.25. Okay, and so we're just going to have to tell you basically something that's true. That basically our focal width for a hyperbola is...
sorry, yeah.
Our focal width is 2b squared over a. Okay, that's what our focal width equals. I think we're going to get there from this. So 281.25, that's half of our focal width. So to get our whole focal width, we need 2 times that.
Right, which only makes sense because we're going down the same distance that we went up.
Right, so what's 281.25 times 2?
17.
Not so much.
I'll punch it in. Whoops, that's the camera ones.
562.5.
Wow, how did you do that?
Oh, magic. So that means that we have 562.5 equals this focal width, which is 2b squared over a.
562.5.
Okay, thanks.
Okay.
So we can multiply both sides by a, perhaps, to get a slightly nicer looking formula. Okay, so that means...
That's a really big 2.
So that means that now we've got a system of equations that we can solve for a and b.
Dogs.
So, which of these is a better situation? Neither of them.
I think-
Secret option number 3, A equals C minus 90. No, wait, because then we've got B. That's still not helpful. But we know that B equals what with our Pythagorean relation?
I don't know. What does B equal with our? Do
C
we know
squared
C?
minus A squared?
Oh yeah.
All right, so
No, plus for the hyperbola, isn't it?
It's
plus?
A squared plus B
okay.
squared
No, I
equals-
got you. All right, right.
it's
right,
A squared plus B squared equals C squared. So if I solve that for B, I would subtract C
Yeah,
squared.
gotcha.
So 562.5A equals 2 times square root of B minus A squared. Hey, that's convenient that we're squaring that. That gets rid of that square root.
Oh, thank heavens! I thought you were gonna have me punch in something on my phone again. You know, my iPhone doesn't have a square root thingy on it. See?
You got to turn it. Flip. No, just a 90-degree turn. There you go.
Son of a gun! Look at all that.
Look at all that stuff.
Whoa.
All right, now
What's an E?
now we can take A and plug it in here. Do you agree?
I agree.
Or should we take C?
Doesn't
Because
matter.
then
We're gonna
there's
have
less
to
to
square.
plug in.
We're gonna have to square something at some point. So
Let's do C.
okay.
So C equals 90 plus
90
A.
plus A.
Which we had earlier written down. So we can work that out. We
Yep.
can plug that into our calculator.
We can do all kinds of great stuff here. But one thing that you can do is go ahead and get rid of that too. So we're back to 281.25 equals 200.25a equals, and then if you square that guy, that shouldn't be hard to square out. Okay, 8,100. Okay, plus
180A.
180a plus a squared minus a squared.
So the A
so the
and A squared and
the
the
a
A-
squareds are gone. So look.
That's actually really
Yeah,
convenient. So now we can subtract
Right,
180A
like we thought
over
it was going to be
and then
horrible,
divide.
and it wasn't. So 281.25 minus 180 is 101.25.
And then we're going to divide that over to the 8100. And that'll be A.
8100. Whoops. 8100 divided by 280.
101.25.
80.
Hey, wow, that's really nice. So A is 80. Now we're just going to do a chain reaction here probably to find our other things. Like we can know that C is 90 plus 80. So that means that C is 170.
Right.
And then once we know A and C, we can plug that in here and get B.
Right. Well, once we know A and C, we can find eccentricity.
Well, we're going to have to do both.
Oh, okay.
Right? So C squared minus A squared, do 170 squared minus 80 squared, and then square root it. Hey, you.
Boy, I don't have that kind of calculator. What'd you say?
C squared, 170 squared minus 80 squared. Yeah, this is hopeless.
Okay, hold on.
No, minus 6,400.
Hold on, hold on. The Inspire to the rescue. What is it? 80 squared? It's 170 squared. Minus 80 squared equals square rooted 150.
Okay, so ABC.
How did you get that already?
And now E. So C over A. So 170 over 80, which you can get rid of the zeros, and that's 17 over 8, which as a decimal.
17 over 8 as decimal. I learned how to do this on my calculator. 2.125.
All right, so we've got A, B, C, and E. Now, what are the coordinates of the center of the sun if we coordinatize space so that the hyperbola is given by this standard form with the center of our hyperbola at 0, 0?
Do we have to run this
So-
past NASA if we coordinatize space?
I don't think so. I think it's okay to coordinatize space in general.
Can you even say that word?
Apparently not. So the sun is the focus. So
Which is C units from our
and
center.
the way we have it set up, it's positive C
Right,
units.
right.
And so our C is 170, so it'd be at 0, 170.
Right.
Ta-da!
There you go.